set of BW plus
Okay.
1 to 1.
Hello, everyone. Welcome back. Any questions before we start?
Are we going over the exercise?
Yeah, let's go over some of the exercises. Yeah, let's go over the exercises. Okay, so if M has a monoid structure, then M times Y is an applicative or a tensor monoid because you have these various contributors. Each one's contributing an element of M, and we need a way of like combining their contributions. Well, we have one because M's a monoid, and given a return, there's only one return, like nothing. You don't get anything back, so you just get an element of the hum of existence back or whatever, and it goes back. So, sorry. So My, if M is a monoid, we have a map from My times My to My, and a map from Y to My, and they're associative and unidal, and so nothing's really happening there. Just use the monoid structure. For any set S, there's a map like this because on positions, it's got to be 1 times 1 to 1, and on maps back for the returns, someone returns to you an element of S, and you need to return to each of your contributors an element of S, and it turns out the only thing that'll work is the diagonal. And the only thing that'll work here is the terminal thing. Now, down here, maybe a lot of you didn't get here, but P tensor Q is always a tensor monoid if P and Q are. So now we also know that like My to the S, which is My tensor Y to the S, will also be a tensor monoid. So if we have some tensor monoids already, some applicatives, we can like form new ones from old ones we already have. So you could take anything we're about to do and like hit it with any other one we're about to do, and you'd be able to form new ones. So let's do the third one. So someone comes to us. We have a set of U. Let's say U is the set of all strings. And now you've got these, and then, so we have this power set of U here, power set of V. Okay, some people didn't know the symbol. That's the power set of V, the set of all subsets of V. Okay, so we've got this collective of people, and they're all allowed to contribute some set of strings. So I contribute the strings Topos and Institute. Nate contributes all strings of length less than 12. Everyone just contributing a set of strings. And so what we do, we need a way of turning that into a set of strings. And so there's actually 3 different suggestions that were given that I think all work, although I only have checked one of them myself. So the one I chose was, let's just union the strings I chose, Topos Institute, all strings of length less than, let's say 6 or whatever instead of 12. That way Institute will be, okay. Topos and Institute, all strings of length less than 6, and the word yay. We take all those contributions and we union them up, and that's what we do on positions. And then some selector person chooses a subset of the contributed strings. They point to some of the words, all the words that they like. And our job is to send them back to each of us, to a subset of the ones we picked. And so a valid way to do that is to send to me, if they picked either Topos or Institute, send it back to me. Just to take the subset, so we take V1 and V2, and we send it to V1 union V2. And then if somebody gives us a subset of that, we send it back to each of us as V2 intersect W and V1 intersect W. So just that's an applicative. That's a tensor monoid. That is a lax-monoidal polynomial functor. So for each of these, we have a lax-monoidal structure on this functor. That's the same thing as being a tensor monoid. So did anyone get number 4?
Before we get to that,
yeah.
Just a question. Like a monoid in a category of functors is always a monoidal functor?
A monoid, well, the word monoidal functor has a meaning already, like a lax-monoidal functor.
Yeah.
And so if you use this term, then you have to be careful of what monoidal structures we're talking about.
Yeah.
But it is true that a tensor monoid, so if P is a polynomial and we have a map from P tensor P to P and Y to P, the question was, is this a monoidal functor? Well, monoidal functor from set to set, a functor from set to set is called monoidal if it's called lax monoidal if there's a map from 1 to f of 1 and from f of A times f of B to f of A times B. This would be a lax monoidal functor from set, the Cartesian monoidal structure of set with times, to set with times. We need these two structures, and they need to satisfy some reasonable compatibility conditions. And it turns out that you happen to get it right, that maybe you knew this, that a tensor monoid will be exactly a lax monoidal polynomial functor. Like, if this is, yeah, so yes, this is a lax monoidal functor. If P was a times monoid or a plus monoid or something else, it wouldn't be what people normally would call, like, I mean, it would be a monoidal functor for different things.
Right.
Yeah.
It would still be a lax monoidal functor, though, right?
It would still be a lax monoidal functor of some sort, yeah.
It just wouldn't be.
For times. Yeah.
Times.
Yeah.
Okay.
Yeah. I don't know about plus. Plus monoid would not be a lax monoid. I think, yeah. I think a plus monoid would not be a lax monoidal functor of any sort. There's no data in a plus monoid, remember? A plus monoid was just a polynomial, so it doesn't have any extra structure. But a times monoid will be a lax monoidal functor with plus here instead. I don't know. So I'm not trying to go into this, but the answer to your question was yeah, in this case.
Yeah, I have a question which came up with actually number 3, but
Yeah.
But I think is more emblematic of a lot of issues that I run into when applying this stuff.
Yeah.
And I'm interested in how a mathematician approaches this issue that I'm going to mention if I could, because
Okay.
I think it's a big barrier for many of us.
Okay.
And you seem to, not surprisingly, not suffer from it at all.
Well, okay.
So the issue is that I find in quite a few cases I get bogged down in the notation. Like,
Yeah.
how do
I definitely get
how do
bothered
I
by it.
indicate this?
Yeah.
But it prevents me from
Doing the work.
doing the substantive work
Yeah.
of like seeing it through to an answer.
Yeah.
It's like this how to name it and how to notate it
Yeah.
gets in the way of actually solving the problem. Whereas I sometimes get the sense that you press forward and at the end of the day you're not particular about the notation. Maybe it's not quite right, but you see through to the answer. Boom. And you cut through to it. And you don't let yourself be bogged down and loaded down by this notation.
No, well, I sit in my room and I work and work and work until like the notation's good enough to carry me to an intuition.
Okay.
And then once I get the intuition, then I start to get a better notation. I like, oh, this is the notation I'm going to need. And then back and forth until like it's clean.
But
That's
you're
kinda
willing to push forward even though the notation is not.
Yeah, I'm getting more and more blind, and I'm like groping more and more.
Yeah.
But you work with easy examples, and and you just try to make your way and try to keep improving the notation.
Yeah.
Yeah.
So I guess that's a good lesson to all of us that we shouldn't let sort of the intuition for solving the problem and the key insights be shortchanged by or have a showstopper just because we can't finalize the notation.
Yeah. I mean, type theory is for that. Type theory is for making the notation so clean that you never have to question it, and your computer can run on it, and that's what they're doing.
Okay.
Yeah.
Okay, that's.
And there's some range of people. Some people don't need any notation. They're just like Ramanujan or something. And they're like, oh, well, I know the answer. I don't know how I know. I just know.
Right.
And they're right like 99.9% of the time.
Right.
And you don't know which point one it is.
Yes.
You can never check.
Yeah, but yeah.
Okay.
There are other ways besides this plotting
Right.
way. But yeah,
Okay. Thank you.
Yeah.
Thank you.
It's hard
it's hard. Yeah.
to get the notation right.
Yeah.
I wanted to go back to the previous
This one?
Or not to that, but so because the plus is trivial.
Oh, plus monoids? Yeah.
Does that mean that there's no like alternative?
No, alternatives are times monoids. We'll get to that soon.
Oh,
Yeah, yeah.
We're in applicatives now.
We're in applicatives now. Then we'll do co-applicatives, and then times monoids, and then times comonoids. But times comonoids, they're as stupid as plus monoids. Remember, there's no interesting thing about monoids in the co-Cartesian monoidal structure, and there's nothing interesting about comonoids in the Cartesian monoidal structure. But there are interesting times monoids. Functional programmers call those alternatives.
I'm sorry, could you restate that broad rule? There's nothing interesting about.
If you have a co-Cartesian monoidal category, then every object has a unique monoid structure. You have a map from 0 to any object. You have a map from C plus C to C for any object. And the laws force you to make this the fold map.
And it's a boring one.
It's always boring. There's always exactly one.
What is co-Cartesian monoidal?
It means that your monoidal, co-Cartesian monoidal means your monoidal structure is plus, is coproduct.
Okay. And if it's Cartesian,
then there's no
every
interesting.
Object trivially has a unique comonoid, and it's boring.
Yep. And I think one reason mathematicians didn't study comonoids for a long time, or they're less studied, was because in a lot of categories of interest, they were thinking about times as their monoidal structure.
Thank you.
Okay. Who wants to keep going through these? Like, do you find that interesting enough, or should we move on? I'm kind of feeling like moving on, but I would go through them if you wanted to.
I would like to go through 5.
Through 5. Okay. So imagine you have these interfaces. Everyone's contributing a vector field on R2. And what they want in return is a point. Okay? So 3 different people each contribute, or 4 people, let's say, everyone in the front row just gives a vector field on R2. So they say, I mean, we usually think of this as like some kind of flow, but I want you instead to think of it as what direction you'll walk if you're at a point. You're at a point, this tells you like which point to walk to next. Okay? So the 0 vector field means stay where you are. We're going to add whatever, you're going to add the point you're at plus the vector that's there. Okay, so Larissa contributes a vector field, Max contributes a vector field, Xiaoyan and Nate contribute a vector field. What we do to get the combined one is we take a point. Larissa said walk this way, we walk there. Max said walk this way from there, we walk there. So we kind of jump, 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 jump. And we get, for that original point, we get a new point. And whatever point we started at, we get a new point. So we got a vector field this way. So we combined our vector fields and got a vector field. Now some person gives us back a point in return. And the point we give Larissa is that point. The point we give Max is the result of doing Larissa's vector field to it. So we kind of give the trace of that point as it walks. And that's the points we give back to each of those people.
So, but wouldn't...
And that will be a lax monoidal structure on this polynomial.
So,
Or a
composition would also work. The composition on V as a function, and then the point you give back is just you start with the identity. And the thing you give Max is the identity composed with the vector field that he gave, and then
it might work. I don't know. Like creating applicative structures or tensor monoid structures on this is just a matter of coming up with something from your imagination and then checking the laws. So you just have to tell me how you're going to return points, and it might work.
Then the composition is at least monoidal.
Yeah. Composition is a monoid on the positions. Yeah. Okay.
And David, could I ask another silly question?
Yeah.
So that guidance you gave for distribution there, where you first give Larissa the point itself, and you give Max the
result of doing Larissa's vector field.
Exactly.
Yeah.
So that hinges on having some sort of ordering imposed.
Yeah, this is not a symmetric monoid or a commutative monoid. It's a non-symmetric one, just like that very first one we did where you had the column of water or whatever.
Right. And where is that? Where's the nub, the nugget of where that?
Well,
the fact that we have an ordered set. We don't just have a set of people who contributed. We have
an ordered set.
Okay. Yeah.
So we have this times operation, right?
Yep.
But we also have a swap operation because tensor is a symmetric monoidal structure.
Okay.
So this is comes from the symmetry of the monoidal structure. The monoidal category is called symmetric or braided if you can always get a map like this.
But we didn't say it had to be, did we?
Well, poly with tensor is symmetric.
Okay.
Do you agree that?
Got it. Yeah.
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 That there's an
yeah.
isomorphism here?
Yep.
Okay, and then we could do our times operation.
Yeah.
And you could ask, does this commute?
Yeah.
And if it does, you would say that this operation is commutative, and if it does not, you would say it's not commutative.
I see.
And this, the one we just said, is not commutative.
Right. Okay. Okay. Thank you.
Sure. Okay, so I want to go next into co-applicatives. So this would be a tensor comonoid. So suppose you have a polynomial p, and you have two things. You have a map from p to y, and you have a map from p to p tensor p. And these satisfy those, those conditions that we've written down before, the comonoid conditions. I could write them in commutative diagrams if you prefer, but just look at these and say, as we usually do, we're just going to look at these and try to come up with things that feel sensible enough that we just believe these. And then at home, if you're interested, you would go home and check them.
I'm sorry. Could you pose the question being asked?
I'm saying let's now look at tensor.
Yeah.
What are tensor comonoids like?
Got it.
So here's the strategy. The strategy is that mathematicians have told us that in tons of different categories, if you have a monoidal structure,
Yep.
you will be interested in the monoids and comonoids.
Yep.
They just say, hey, you're looking for something to do with your time? Go check out, if you want to dig for oil, you go to the places where you think there's going to be oil. Well, there's going to be, they tell us, category theorists or mathematicians tell us that if you have a monoidal structure, go check out the monoids, go check out the comonoids, and see if you can mine something of interest. And that's what we're doing. So we're like, okay, tell me about the comonoids in poly, the tensor comonoids. And so to give one is to give a natural transformation from p to y and a natural transformation from p to p tensor p. And these should be sensible in the sense that, like, they're co-associative and co-unital and that sort of stuff. And what that feels like is that it's not weird. It's like not completely contrived. And when we looked at this thing, and when we were looking at tensor monoids, and like somebody contributed 7, and somebody else contributed 12.5, and that was 19.5, that felt pretty normal. And then we get 16 back, and we give 7 back to the first one, and the rest back to the second one. That was like, is that going to be associative? And you can check that. But it's like sensible enough that you might believe it, and you can go check it at home. And so that's what we'll do here also. We'll talk about tensor comonoids and see if you can see what they are.
Can you explain the little string diagrams again?
Oh yeah, this one says that I have a map from P to P tensor P. That's that little thing there. So I have like P to P tensor P. And then I have a map from the left-hand side just to Y, to the monoidal unit. And from the right-hand side to P itself by equality. And so the map to the monoidal unit I draw this way. And the map to the tensor product I draw that way. Yeah. And so you just kind of start drawing pictures. And these equations turn into commutative diagrams. I don't know. Is that helpful?
Yeah.
We can talk about it later, but yeah. So if you split, and then you take one of the two factors and you terminate,
yeah,
that's the same thing as not having done anything, as the identity on P.
Yeah.
That's what this is saying. And this is saying, oh, terminate the other side. And this one's saying duplicate one, and this one's saying duplicate the other. Okay. 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 So what happens if you have a map from P to Y?
It feels like you have to have a sensible choice of direction.
You have to have a sensible choice of direction for every position.
Yeah. So like every direction has to be a monoid?
Every position, every direction set has to be a monoid?
Yeah.
Okay. Well, here's one thing we know. We know that if we take positions, p of 1 to 1 and p of 1 to p of 1 times p of 1, that since the functor p of 1 is strong monoidal, it sends monoids to monoids and comonoids to comonoids. And so if you apply 1 to this thing, this has to be a times comonoid. I know I'm probably going too fast. I'm going to get to what you're saying. If you just let it, I don't know. You have to watch it on the tape again later. But there, I said before, in any Cartesian monoidal category, times monoids are trivial. There's exactly one possible way. So what I think you're actually saying, without meaning to, is the first step of what you're saying is that on positions, nothing interesting can be happening here. It's going to have to take the position and duplicate it, and just kill the position. So yeah, on positions, all this is going to do is duplicate positions. And then on the way back, you've duplicated the position, and then you need to map back a single direction, and you need, for any two directions at the same point, at the same position, you need a direction. And so you're exactly right. This is just like a bundle of monoids. So Andre's intuition was that all that's happening here is that we have, remember, a polynomial can be thought of as like you've got a bunch of positions, and for each one you've got a bunch of directions, right? And the point is, every one of these positions gets a certain direction coming from here. And given any two directions, you can get another one. And somehow they're associative and unidal. And so he just guessed maybe this is just a bundle of monoids. In other words, each of these things is a monoid. Monoid, monoid.
When you say bundle, do you mean
well,
tensor bundle?
I just mean like we've got all these positions. Yeah. For each position, we have a set of directions. Yeah. That set of directions is a monoid. Yeah. So that is let A be a set. Suppose you have a set. And M is a function from A to monoids. Yeah. A functor takes every object in A, every element of A, to a monoid. Then the polynomial sum over A in A, y to the m of A, is a tensor comonoid. Do you want a minute to think about that, or do you have questions?
Yeah.
Yeah.
So what did you do to, so you said you incanted something between that top statement, epsilon and delta.
And then this one?
And you got that thing below. There was some magic spell you cast.
Yeah, I can't.
Is that the deconvolution of product?
So what I did is I said that.
Yeah. Or is it just you reasoning about positions?
I said that there's this functor that takes a polynomial and returns its positions, p of 1.
Yes.
P on the one element set.
So it's a functor.
That's a functor from poly to set.
That just like applies it to 1.
Applies the polynomial to 1. It's one of the things we do the most often, right? We always do that. We want to take the positions of our polynomial. It counts how many summands are in the polynomial, which is our favorite thing.
Why not?
Well, this is strong monoidal. It's strong monoidal, meaning that it sends y to 1, right?
Yeah. Yeah.
And it sends tensor to times on the nose. Like it takes the polynomial p tensor q, and when you look at its positions, it's p of 1 times q of 1.
Yeah.
And so this being strong monoidal gives us a fact. It gives us a fact that any tensor monoid is sent to a times monoid, and any tensor comonoid will be sent to a times comonoid. Cool.
Can you do the?
And therefore, we knew that on the underlying sets, this was just a times comonoid. Yeah.
Can you give us like a real concrete example of a polynomial of a tensor comonoid for very specific polynomial?
Yeah. Y to the nat. Y to the natural numbers. Or y to the natural numbers plus y to the list of bools.
Wait, can you walk us through one?
Okay. Which one? Okay, this one.
Yeah, that one.
Okay. Let's show that y to the list of bools plus y to the nat plus y to the, does anyone know another monoid?
Free monoid?
I already did that one. I did. I kind of picked the same one twice. I'm annoyed. I picked list of unit and list of bool, so I feel dumb.
Can you use strings?
Z mod 2. String is also list of characters.
Okay.
So we need like some non-free monoids.
What's the bool? Just bool.
Yeah, bool. Bool under
Sure.
under or.
Yeah.
Okay.
Yeah.
Okay, so let's prove that this thing, give me a map from P to Y. So let's say P is Y to the nat plus Y to the,
Wait, why did it nat?
Sorry.
Changing it to nat?
is it, I don't know, it doesn't matter.
Yeah, it's
They're all the
less
same.
characters, yeah.
They're all the same, okay. Y to the bool, okay. Okay, let's prove that there's a map, let's figure out a map from P to Y. So on positions, it sends every position to 1. And so given a direction, given the unique direction here, I need to pick out a direction of nat and then direction of bool. Yeah, let's pick out, let's send it to, yeah. 0 and false, yeah.
Okay.
So it sends, yeah. Yeah, I understand it's annoying to notate these things.
Yeah.
Does someone want to see me try because they want to see how me go through the pain also? Or yes?
Yeah.
For real? Okay, fine. So I'm going to, yeah, okay. Y to the nat. Yeah, how do you do this? So if you have type theory, then you have all this stuff that you need. So let's just use polyboxes, I guess.
Yeah.
You're going to do P.
So so we pick, yeah, it's annoying. Yeah. Okay, we pick 1 or 2. Like we pick either the summand here or the summand here. And in this case, 1 and 2. And in this case, we have bool. Okay, so and then y is just like star. This is like awful. Sorry, guys. I didn't expect to have to do this. This is confusing and pretty bad. Yeah. So where do you want to? It's just terrible. It's just terrible. Okay. So let's call this thing phi. This is what I get. Epsilon. Epsilon 1 takes. I have two choices. I either take.
Wait, it makes
Yeah.
sense because you have to kill everything. So you have to send everything to the monoid unit with it via like the loop because you have to choose an element.
Yeah, but it's hard to draw.
Oh.
It is hard to draw. So 2 goes to the unique element of unit type, or however you want to write it, 1 or bang. See, the problem is there's so many choices in how we're notating elements of everything here that it's very personal. Like in type theory, it's not personal. You've exported and told everybody how you're going to notate everything. But in math, we typically are living, we're living in intuitive land that we share through theorem statements and not through notation. And so it's kind of like a personal feeling how I want to notate these things, and I don't expect anyone else to necessarily be able to read that, especially if I haven't prepared like in advance.
Can you use
But-
the phi 1, phi sharp?
Yeah, so phi 1, okay, good idea. Phi 1, epsilon 1 is bang. It takes every position here to the unique position there. Okay, epsilon sharp of 1, which is this one, is a map from 1 to nat, and epsilon 2 sharp from 1 to bool is like that. And so I just need to pick a natural number, and I need to pick a Boolean. And Andre's intuition was that we're supposed to pick the unit of the monoid, so 0 and false. Sorry, everyone, for the delay. I think we're back on track.
Yeah.
Thank you for the suggestion of using the notation that we talked about from the very beginning. Okay, so now delta is supposed to go from P to P tensor P. So we need delta 1 that takes P of 1, which is a 2-element set. The 1 and 2, I guess. And we need two 2-element sets. I mean, we need an element of 4. So we send 1 to 1, 1, and we send 2 to 2, 2. Because we know that on positions this has to just be diagonal. Okay, so this is the component of delta at 1, and then delta sharp 1 and delta sharp 2. This goes from 2 times, no, this goes from delta 1 goes from nat times nat to nat, and delta 2 sharp goes from bool times bool to bool. Do you guys agree?
Yeah, oh, so you just
And
whatever monoid.
and I use the monoid structure. Yeah. And there's nothing else like, so what we get is that every position must have a monoid sitting over it. Yeah.
And so if you have that, that's also always a tensor comonoid.
Yeah. A tensor comonoid and a bunch of monoids is the same thing. Yeah. It's just a bunch of, so what this feels like is that you have this P. If we want to draw this in box land, you have this P, and you can absorb, and you can always in a wiring diagram kind of do this thing, but Sophie yesterday drew something where they come in also. And in a tensor monoid, you have that because the inputs can be monoided together, can be added or, appended, smushed together.
Sorry, can you say that again?
So in any wiring diagram, you have these Moore machines or dynamical systems, and they're sending each other data, but they can split anytime that you want, right?
Yeah.
But they can't merge because we don't know what that means.
Right.
But when you have a polynomial that's a tensor comonoid, it turns out that what that means iconographically, like in terms of what you can draw in your picture, is that you are allowed merging.
Right.
Because this thing understands
Yes.
how to take inputs.
Yes.
Whatever its output is, it knows how to take its inputs and
Yeah.
add them together.
Yeah.
Yeah.
Is there a convention that I'm
So yes, sorry, one last thing. Yesterday, I think Sophie had this, right, in her picture. And she said, and assume we're going to take our inputs and add them. Well, that's
Right.
because this is a tensor comonoid.
Oh, so it's like the wiring diagram for delta, but on directions it goes backwards, which is then just the wiring diagram for a monoid.
Yeah.
But on directions.
Yeah, exactly. Yeah.
Okay, that makes
Yeah.
sense.
Yeah.
Is there like a convention for wiring diagrams to like maybe notate a wire differently when the type there is a monoid, and then if every input wire to a box is a monoid, then that is a
Yeah, that's okay. You can do that too. Yeah. That'll work. Okay, any questions about tensor monoids and tensor comonoids? Tensor comonoids are much easier things than tensor monoids. Tensor monoids are very rich and like, what are they? These collectives of things contributing and getting returns. These are just very simple. We don't care what's going on in the positions at all. And on the directions, there's a monoid at each position. Yeah.
I think I'm just trying to situate this. So, David, you had said that you can't have these, with the, for the normal case, you can't have wires coming together.
Right.
When you have tensor monoids, you can have wires coming together.
When you have tensor comonoids,
To have them come together?
yeah, because remember on direction, so remember this is like input, right?
Yeah.
Which is like directions.
Right.
We call those direct. That's a tensor comonoid. Its directions are monoids.
Okay, it's directions monoid. And I'm just trying to situate this. Sophie had this wonderful paper and talks about, understanding undirected wiring diagrams and directed wiring diagrams with the different mathematics. This is directed wiring diagrams.
Yeah. Mm-hmm.
Because you distinguish input from output.
You can distinguish.
And
Yeah.
you've made famous and compelling some examples like electrical circuits and so on, which use undirected wiring diagram. The things just flow along the wire. If they're connected, if they come together, it's the same value. Okay. I just wanted to.
Yeah.
Yeah. Thank you.
Sure. Yeah. So tensor monoids, kind of like, we kind of drew this weird picture where you had something coming in and splitting to a bunch of different ones inside. We had this picture on the board before.
Right.
And we said like somehow you could use this data to do this distribution. That was this kind of weird, bizarre picture, but it kind of makes sense. Do you remember this? It's like all these different, for the tensor monoids, all these different things are contributing positions, and so we can aggregate them. But then we can use the data of who contributed what. When we get something in, we can use it to distribute.
Yeah.
So that was like a very kind of surprising thing. And it's hard to notate. It's very surprising. This one's really easy. It's just saying that like you can always split wires, but when you have a tensor comonoid, you can also merge them. Or it's just saying like you have a map from P to P tensor P. So if you, I don't know. Yeah, if you have a map from, I mean, all I'm really saying is if you have a map from P tensor P to Q, you have a map from P to Q. If your wiring diagram had two P's in it, you can replace it with just one P. And this kind of is shorthand for how that kind of feels.
I have a comment and a
Yeah.
question. The comment is that this thing that is hard to notate with
Yeah.
like having to list the different components of the sharp is actually very nice in Agda.
Oh, really?
Maybe it is also, yeah, because you notate with where you came from on the type signature of just
Yeah.
a polynomial in general.
Right.
So like your case splitting makes it very obvious when you're doing the direct math.
Cool.
And the question is, you can just say a word. Like it was a word that allows the input to go straight through that we haven't gotten to yet. When you have an input, right now we don't have the technology.
Oh, Mealy machines?
Yeah, maybe.
Maybe, yeah.
Yeah, because the boxes are Moores.
Yeah.
And when we get to Mealy's,
Yeah. Yeah, I kind of want to move on to, but I guess I should go and just talk about like in order, which are times comonoids and times monoids. So do you guys remember what a times comonoid is? It's a set, it's a polynomial P. We're on to the next monoidal structure here. And tomorrow and the next day we're going to spend all the time on the substitution monoidal structure, where you can take two polynomials and you can substitute one into another. That's the richest one. It's not symmetric and it has all sorts of amazing properties, etc. Or it gives you all sorts of crazy structures that you're not expecting.
7 wonders.
7 wonders of the composition product, yeah. Okay, but times is an easy monoidal structure. You can take any two polynomials and multiply them. And so we can ask, what are the times monoids? What are the times comonoids? Do you remember what's the unit of times? 1. Yep. So I need a map from P to 1. I need a map from P to P times P. And so for a times comonoid, does anyone know what it is?
is everything?
Yep. Every polynomial is a times comonoid in a unique way. So for any Cartesian monoidal category, and poly is one, the objects, polynomials, every object is a times monoid in a unique way. So that's not interesting. I mean, it's interesting to know that there's nothing to see here. It's good to know we've mined this mine. There's nothing more to look at there. No oil there. So the last thing to do is tensor monoids. This is not like a like series finale. Like this is not the big fireworks display. This is just another thing you can do. It's pretty interesting. I find it pretty interesting, but it's not. I think the I mean, the most interesting will be the substitution comonoids and monoids. Those are called monads and comonads. This is kind of interesting. These are called in Haskell. I think these are called alternatives. And the reason, yeah.
Well, it's in Haskell, alternative is a lax monoidal functor from category with plus and 0.
Yeah.
One with times and
Yeah.
1.
So these things, what you're going to get is because times is the day convolution of plus, and I'm not expecting you to know what that means, but because times is the day convolution of plus, there's a map from P of A times Q of B to P of A plus to P times Q of A plus B.
Wait, times is a day convolution of plus?
Yep.
And tensor is a day convolution of times?
Yep.
Okay.
And what this says is if you take, maybe you could agree, if you have P of A and you have an element of Q of B, so if you have a position of P and for every direction an element of A.
Wait, say it again.
If you have a position of P and for every direction there, an element of A. That's an element of P of A. So I have a position of P and for every direction, an element of A. And I have a position of Q and for every direction there, an element of B. Do I have a position of P times Q? Yeah, because P times Q, the positions are a pair of positions.
Yeah.
Okay, what are the directions of P times Q? The sum of the directions of P and the directions of Q. So if I have an element of that sum, it's either a direction of P or it's a direction of Q. So suppose I give you a direction here. Do you have an element of A plus B? Yeah, because it either was a direction of P, in which case you have an element of A, or it was a direction of Q, in which case you have an element of B. And so I think the reason these are called alternatives is because if P has this structure, this is true no matter what P and Q are. But if P has this structure, then we have P of A times P of B. Give an element of P of A and an element of P of B. We get an element of P times P of A plus B. But then because of this structure here, we have an element of P of A plus B. So it says, if I have a position of P and for every direction, if I have an element of P of A, an element of P of B, then I have an element of P of either A or B. It's like this alternative thing. Maybe Solomon can give better intuition for why it's called alternative.
You've got two alternatives.
Yeah, yeah.
I'm still I'm confused about this. Wait, what is P and Q are polynomials here?
Yeah. Yes.
And what does it mean, P parens A? What does that mean?
You apply the polynomial as a.
Oh, this is a polynomial as a functor. Okay.
Yeah. So let me just give you like a bunch of these times monoids, and we'll like pick a few to go through, and just like go until we feel tired of it, I guess. And then we'll move on to either take like a break and consolidate, or we'll go on to closures. So there are monoidal closures, and those are interesting, and we'll do that as our last thing today.
Solomon, could you say that again? That the in Haskell alternative is a lax monoidal functor from set times to set plus? Is that?
Yeah, well, you've got to pick an identity.
I guess it's written right here. See?
Okay.
The identities are void and unit.
Okay.
There's a couple ways of
From either void to tuple unit.
Ah, okay. Gotcha.
See, we can see it here. Given an element of P of A and an element of P of B, we get an element of P of A plus B.
And then
So this is a lax monoidal functor from plus to times, I guess.
From times plus.
From plus. This yeah.
and then
Because of the way they call it. This would be a lax monoidal functor from. No, what? Whatever I said before was the right one.
one it's yeah, that's right.
Yeah, that's right.
And then 1 and times. And then if it's offset, you get divisible and decidable.
So another way to see this is that a polynomial is a functor from set to set, right? but every monoid has an underlying set. P is a tensor monoid, is a times monoid if you can lift P to monoids. Every element of set gives you a monoid. Probably your eyes are glazing over, so why don't I just give you a bunch of examples. So examples. Suppose that M and N are times monoids. You don't know any times monoids yet, but I'll start by telling you some. So first of all, I'm not going to use these for a little while. M is a times monoid if it is a set monoid. Like if it's a regular old monoid like Nat or Boole, then this constant polynomial is a times monoid too. So first of all, we have some very basic times monoids. List is a times monoid.
What is list as a polynomial?
Oh, right. List is the polynomial 1 plus y squared plus y cubed. So like list of bool is like the set of all lists of bools.
Oh,
It's either an empty list, or it's a Boolean, or it's two Booleans.
Yeah, it keeps going into infinity.
Yeah. So it's the sum over all natural numbers of y to that natural number. Okay. And that's a times monoid. Maybe we should check. Do you guys agree that there's a map from M times M to M if M is a monoid? Yeah, because that's what it means to be a monoid. Do you agree that there's a map from list times list to list?
Yes.
I mean, clearly giving a list and a list, you can get a new list because what you would do is concatenate them.
Right.
But what if I give you a direction of that list? In other words, I point at one of the elements of that list. Can you give me a direction of either the first or the second list?
You just point at the list where it came from.
You pointed the list where it came from. Yep. So what this does is, as a polynomial map of polynomial functors, it doesn't just give you a map from list of A times list of A to list of A. It gives you the map back on directions that says what do you want to point at, and it points at the right place.
Wait, what do you mean it gives you the list back you came?
Sorry.
Can you explain it more explicitly?
We want to give a natural transformation from list times list to list, right?
Yeah.
So we say what to do on positions, and we say what to do on directions.
Right.
On positions, we have a list. We have a number, the length, and another number, the length,
Yeah.
and we get a number, the length of the sum length.
Yeah. Easy.
And then given a position in that list,
Uh-huh.
that's an element here. Given a pointer to that element, I need either a pointer to an element, an entry in this list or an entry in this list. Because I need to give a direction
How
here.
do you distinguish which list you're pointing into?
Well,
It's a sum.
so okay, let's just write it then. So you have m comma n is going to be sent to m plus n, right? And then if somebody picks a number n between 1 and m plus n,
Yeah.
we're supposed to give them back either a direction here or a direction here.
Yeah, but how do you know which?
Right. So we'll give them back n. We'll give them back 1n if n is less than m,
Oh. So
and
it's-
2n minus m if n is bigger than m.
So so you have to. The order matters.
The order matters. This is not a symmetric monoid. They're a commutative monoid. Yeah. Okay. Yeah.
That's neat.
Yeah.
You want to do maybe?
Do I want to do maybe? Yeah, I'll.
Maybe.
Thank you. 3. For any polynomial p, p p plus m. M is a monoid already, is a times monoid. So I just did maybe. How did I just do maybe? Oh, by the way, maybe monoid is called y plus 1.
Yeah.
Wait, what?
Where'd that come from?
Okay, sorry, this is a Haskell term. They call it the maybe monad or maybe. It's the polynomial y plus 1. It sends a set x to either x or fail. Like if I say divide by 5 divided by blank, and I don't know what natural number this is, I get a maybe rational. I either get a rational or I get fail. Yeah. Okay, so does anyone see how I got picked up maybe with example 3?
Yeah, because we want m is 1.
Take m to be 1 and p to be y. But why? Okay, should we try to? I don't know whether to move in, like prove this is a times monoid.
That's
Or
magic.
Yeah, it's kind of magic. Yeah, there's tons of ways of getting times monoids. Should we prove it or should we check it? See it? Okay. Can I erase this?
Can I?
P.
I'm still copying it down.
I need a map from p plus m. I need a map from 1 to p plus m.
David, I can memorialize it, and then I'll finish the transcribing.
Sure. Okay, so to get number 3, we need a map from 1 to p plus m, and we need a map from p plus m times p plus m to p plus m. And all we're allowed to use is that m is a monoid. So how do we get the map from 1 to p plus m?
Inject right the,
Inject right, put it into the m.
yeah.
Okay, now we have p plus pm plus mp plus mm.
Well,
Right, I distributed.
oh,
We have 4 cases. So some of these might seem weird, but you can do it, and it works. So let's just do these first. So let's say you have this one, m times m.
just multiply? Just m.
Yeah, m.
Just motion
What
down.
about these ones?
I think the p.
I think you picked the p. How do you know that?
Because the monoid laws.
Yeah, the monoid laws. So functional programmers can just do these things. I don't know how they do it. It's true that you would either pick the project to the m or project to the p. And it turns out we know that if we picked 1, we know we'd be projecting to p. Right? If we picked 1 for our element of m, we know we'd have to be projecting to the p side.
Wait, I don't see that. Why?
We have a map because the monoid laws says that if we pick 1,
Yeah.
we better get back where we started.
Just.
Yeah.
Yeah, so we know that if m was 1, if we came into this m through a 1, we'd have to project to the p side, and like that's intuition enough to guess that we're going to project to the p side here.
Think back to
Now you should go check this yourself. Anyone who wants to should go check for themselves that this is a p. Like I'm just telling you the intuition to get you started. And for this one, we're going to project to the p side, and for this one, you just take the first. And that's what you have to be happy with that because that's what alternatives are about. Alternatives are about.
Just taking the first.
Alternatives are about the fact that sometimes you just want to take the first if you can. So what this says is, if I offer you a p thing and an m thing, either a p thing or m thing, and another either p thing or m thing, if I give you 2 m's, like do your m operation. If I give you just one of the good ones, like
Anything is good.
and then pick the p-ish one I gave you. But if I pick 2, the alternative I want you to do is, and one alternative would be project to the left, and one would be project to the right, and that's 2 different structures on this.
And
2 different alternative structures on this.
The other.
but if you have so last would be
Another
pick
structure.
Pick the second.
Yeah, you could do that too. Okay, another one is mn. Just multiply the 2 monoids. I mean, maybe so mn which means times mn. We need a map to mn. But this is isomorphic to mmnn, and so we can just use the multiplication we had because m and n already were times monoids. So we start with like two very basic ones, and we just start getting all sorts of new times monoids or alternatives.
Wait, sorry, can you do mn one more time? I'm just writing it down.
This one,
You said.
mn?
Yeah.
Well, mn means m times n,
Yeah.
right? MN is isomorphic to MMNN.
And we just
Squish, squish. Yeah, yeah.
And for 3, sorry, just for that one, for the p plus m example, on directions going the other way, you send the direction back to the one that you would take as the alternative.
Yeah,
Okay.
yeah. A lot of these I can't write down because we haven't gotten far enough, so I wasn't sure what to do about that. I'll just write them, and then when we get to it, you'll know what I'm saying. So for any p in poly, m trie p is a times monoid. So trie is what we're going to get to tomorrow, this substitution product thing. And this will be another times monoid. For any p in poly, the inner Hom Pm is a times monoid, is a alternative. When I said you have to like it, I was talking to Solomon in particular, or functional programmers in particular, who want to be calling these alternatives.
Yeah.
If you're working with alternatives, if you want an alternative, then
Embrace them.
you should embrace the fact that you are
Yeah.
taking first. That is what
That's
they're
true.
for. Yeah,
Yeah.
yeah,
David,
yeah.
are those things like these maps from 1 to p some poly and from
What
thing
are you talking about?
times
What a times
yeah,
monoid is?
can
Did I
we,
not get
in
to the-
general,
oh, here.
Would you call those epsilon and delta still?
For monoids, you usually call them. I don't know. I usually call them like E and star.
Okay, got it. Okay, thanks. I'm just trying to.
What is
Yeah.
this square bracket, PM?
We'll get to that in the next. That's our next thing.
Oh.
It's the internal Hom. I know you don't know what it is yet. I wasn't sure whether to tell you, but I'm going. I'll just do it. For any applicative, for any tensor monoid, A. So if A is an applicative, it's the thing we did before. It's also called a collective or a right a laxmoidal functor. It's these like economic collective thing. Remember? Okay. For any of those, A composed M is a times monoid. I suggest like if you're like wanting to just do a little homework or something, or wanting to do some exercises, just see if you can guess how these things work. For any polynomial P, M to the power P is a times monoid. We haven't talked about these yet, so what we're doing the rest of the day is this inner Hom and this inner Hom. But there's just one more. For any monad or trimonoid T and tricomonoid,
Wait, a trimonoid is a monad?
yep, C, T to the C. We haven't gotten to this symbol yet. Try for triangle.
Okay,
Yeah, sorry.
okay.
For any substitution, it's just so long to say substitution.
'Cause when you said,
I
was
know,
thinking
I know,
alternative,
I know.
like try
Yeah,
this.
sorry. T to the C is a times monoid. Okay, these are the ones that I know. Yeah.
I'm sorry, for that one up there, just trying to get it, 1 to p plus m,
Mm-hmm.
are you selecting like the monoidal unit of p, e? or something?
All we know is that M and N are times monoids.
Yeah, okay.
P could be 0 as far as we know.
Okay, okay.
There's no way this could-
I see,
yeah,
I see.
yeah.
So you pick the monoidal unit of m then?
Mm-hmm.
Is that it? Yeah.
Yep.
Okay, thanks.
Yeah, these are weird things, but they exist. And someone like nature says they're interesting, so they're probably interesting. Well, in the sense that they're the monoids. They're like times is even somehow like the most monoidal product somehow.
I like these more because it doesn't privilege the first thing.
Neither does times.
What do you say?
Neither does times. 'Cause times
Yeah, times doesn't privilege. We
Well,
privilege it.
slash.
We privilege either the left or the right. Like they're.
Yeah, but you don't have to do that with these.
I guess I should say like in two ways. Maybe that helps.
For the bottom one, you're collapsing down sequences that are drawn from the same monad?
Yeah. Yeah.
And there really are
That is
two,
delight.
like two instances for each one.
For this one.
Yeah, because like,
Yeah.
you can either alternative prioritize the first or the second.
Yeah.
Yeah.
The first or the last in some sense.
First
If you
or
do a lot of them, you're going to be either privileging the first or the yeah. Yeah. So imagine for this one, you've got not just two, but a lot. Some people are contributing p's and some are contributing like everyone's allowed to contribute either an element of p or an element of m. So a bunch of people are giving out things, some from p, some from m. And what you do is you like keep going through the m's and like you keep multiplying together all the things you got. But if anybody gives a p, you pick it.
Right.
As soon as somebody gives a p, you're like, ah, got it. And the first person who does it, they're the winner. And that's how the times monoid structure wins.
So with
works.
with like maybe is failures, it's like you're actually doing stuff on the specific error messages that you get out until
Yeah.
you get a success. It's like, okay, I don't care anymore.
Yeah, I don't care anymore.
We got a result. we're
Yep,
good.
yep.
This is really common if you think about like for parsing.
Yeah, that makes a lot of sense.
Yeah, yeah. So the comment was for parsing, this is important.
Yeah.
Okay. Any questions about any kinds of monoids or comonoids except for try? Substitution? We'll do because tomorrow and Thursday and Friday is all day this.
I
Yeah.
want to know what you mean. I guess you're going to explain, but what you mean by internal hom? 'Cause
Okay,
when you
that's
say
the next
hom,
thing. Yeah,
Is
yeah.
that what we're doing?
That's the next thing. Yeah,
Because hom makes me think of exponent like hom set,
yeah. Hom set. Yeah.
but this is related to tensoring, right? The
Yeah,
bracket?
yeah.
So how's it?
So we'll get into internal hom. That's the rest of the day. We might take a break between now and then, but yeah. Other than that, we are definitely doing that. Yeah.
I'm sorry, so to go from MNN to the MMNN, those are, you're establishing some sort of isomorphism there, right?
Yeah.
But
Cartesian product is always symmetric
Got it.
monoidal.
Okay.
Yep.
Okay, so you can tweak them, the order,
Yep.
and then you collapse.
Yep.
That's
Yep.
a thing of delight.
Yeah. Okay. Should we take a break? Who wants a break? The mama? Yeah. Yeah. Okay. So since recording is messed up a few times now, we are in this. We're trying to work on closures, and Poly has infinitely many monoidal closed structures. We're interested in two, the one for times and the one for tensor. Those are the only two that I know of as interesting, but maybe if you explore, you'll find that another one was interesting. And what it is it's an adjoint to tensoring with. If you want to tensor with C, there's an adjoint for that. And what we were just saying is a couple things. So this is what it means to be adjoint. It means that Homs in C from C tensor D to E are in bijection with Homs in C from D to inner Hom CE. And that's what this said. But this looks annoying to me. So I kind of wish I'd done it a different way, that tensoring with D is stuff. And what I would say is that Homs in C from C tensor D to E are in bijection with Homs in C from C to this internal Hom thing, DE. Okay. And the way this comes up in like logic is that in logic you have, say, propositions and entailment, and you can like form this new proposition called implies, and that will be an internal Hom. That will be one of these things here. Or in programming, you can take two types and make the function type of all maps from P to Q, and that's an internal Hom in programming or in sets. And And
Universal knob.
yeah, it's the universal knobification or something, yeah. So I probably should say this, like the most important thing you can do, like whenever you have an adjunction, there's a unit and a co-unit. And those are always really important. So before I get to why Poly is Cartesian closed, I should say why, what these most important maps are. And so I'll do that next.
Okay, yes.
So I said that, so set is closed. A function from A times B to C is like a 2-knob function machine. Takes an A and a B and gives you a C. But that's the same thing as a 1-input machine where you give it an A and it pops out a machine waiting for a B. Okay, so that was what we had there.
So that's curry.
That's called currying.
Yeah.
And then the two most important maps are called, well, one of them says that I have a map from C to D comma C tensor D. And that one doesn't come, like somehow, I almost never write this one, but it's kind of there in the background a lot. So why don't we try this for the set case? Do you know the map that takes A to A times B to the B?
Yeah.
Yeah, given an A,
Yeah.
I need a function
Yep.
that waits for a B and gives
Yep.
me an A and B. Okay, that's like apparently important. It's kind of a one at a time way of getting an A and a B, right?
Yeah.
But the other one turns out to be much more commonly found, which is that C, which is a map from C tensor CD to D. And this one is generally called eval. And this one would look like A times B to the A to B. Takes an A, takes a function from A's to B's, and gives you a B. And those are the ones I wrote at the bottom of the board over there also. Okay.
Maybe it's the wrong time for intuition, but I just don't see what is the bracket supposed to contain, like what does it contain?
Yeah.
so to speak?
You mean in Poly or?
Yeah, like what is the polynomial that it looks like?
Yeah, let's get there. Yeah. Okay, so I first want to tell you the Cartesian closure. And for a long time, I never understood what it was good for. I mean, it just seems really important, but like the tensor closure is the one that for me felt like the really useful one. I've started getting more enamored with this one through time, but for a long time I didn't know what I was ever going to use this for in terms of applications and stuff like that, or in terms of thinking about computation or dynamical systems or databases or anything else. But now I just want to tell you what, like if someone tells you that they have a closure, they have to give you a formula for it. In this one, the formula is, say, product over all A and A, B, or something like that. They have to write down a formula. How do you get this magic set? So here I want to tell you, how do you get this magic polynomial? Because in high school algebra, you can take like e to the x plus 1. Sure, you can exponentiate, you know, you can even do x to the x. But like, no one ever told us that if you take a polynomial to a polynomial power, like x squared plus 3x to the power x cubed plus 4x plus 4, that was a polynomial, and it's not. It's a weird thing. But there is a polynomial that works for it, and by works I mean things like whatever we're about to do is going to work in the following ways. It's going to be like 1 to the p is 1, and p to the 0 is 1, and p to the q plus r is p, and these are all isos. P to the q times p to the r, and p to the q to the r is p to the qr times. And like all of the things you're used to, like all the things you're used to, there's probably more that I'm forgetting, but all the things you're used to are true. So it's a little bit weird that you can exponentiate polynomials and get a polynomial, and the one we're going to get isn't necessarily going to feel like exponentiation, but it is the internal hom for times, and it does satisfy all the laws that you're used to. So that's what can you guarantee about it? What do you lose? You might lose intuition about why it's called exponential, or like why it feels like exponentiating when you think about calculus. You don't get that, but you do get that it's a polynomial that satisfies all the rules. Yeah.
So I'm trying to understand your statements from the last minute or two
Yeah.
minutes. I thought you said it's not really this polynomial, but we have something that works.
What I'm saying is like, here's what's worrying.
Yeah.
Here's what like might make you freak out. Y to the y is y plus 1. If that freaks you out and you're like, okay, I don't care, this is this dumbest thing, I don't get why this would be anything, I can't be here anymore, I need to leave.
Unlock the doors?
Yeah, if you feel triggered, then like, yeah, you might be triggered. But this will satisfy all the laws. And there are reasons, yeah.
It's hacky though.
It's not hack. It's a Cartesian closure.
Yeah, but
The lambda calculus works.
yeah.
Yeah.
But it just feels like you were like in a cave and trying to outsmart God or something.
No, God is outsmarting us, if anything.
Why is just
Yeah.
interesting?
What?
Why is
Right, why-
interesting that it just like
Why is it interesting?
yeah like
Why is this interesting?
no like the statement why is interesting.
No question.
Like,
There's no question. Like,
Yeah.
The
why
why,
is
the
it-
left,
why-
yeah, like
why?
the Yoneda like.
Why is interesting?
Yeah, it's
Yeah.
just interesting.
Yeah. Why is interesting? Yeah. Okay. Should
How
we?
is that worse than like e to the I pi equals minus 1?
Yeah. Maybe it's the most beautiful thing in the world. Maybe it's the prettiest. Like, oh, what? Like, yeah. Maybe it's the prettiest thing in the world. Or maybe it's bizarre. I don't know. I think the idea of math is like, or the lessons of the history of math is that often things that felt really wrong to people at first turn out to be very useful, right? So if this is Cartesian closure in a category you love, then your best bet is to learn to love it, more or less, until you can. And if you can't figure out how, then you just wait until you can, and you might wait forever. Okay, so I'll give you the formula for this thing. It's there's lots of different ways to write it, but it's the product over all the positions of Q. Of R. Oh shoot. I haven't given you substitution product yet. That was probably a mistake. I probably should have given you substitution product much earlier. Okay. Positions of R. Product over the directions of R. Of Y plus Q bracket J. So a big thing. So it says, how do you get what is this thing? You product over all the positions of Q, R, this whole thing just says R, of, so maybe I can write it like this. It's product over all the positions of Q of R of, or composed with, Y plus QJ.
That is wild.
It's
And that application you treat as a constant polynomial.
sorry, it's really, yeah. I'm just gonna have to write it.
Okay.
You substitute in for the y in R. You substitute in y plus qj. Yeah. Okay, so let's try to give some examples of this thing.
Thing of beauty.
It is a thing of beauty. It's weird and amazing. So like, what is y
Sorry, I have
to the, yeah.
ask you real quick. Wait, so R to the Q equals blah. What's the line below?
This line?
Yeah.
Are you worried about this symbol?
Well, no, I was writing down the top line and then I didn't hear what you said.
I just rewrote the top line. This thing is R, right? It's the sum over our positions of the product over all directions of something.
Okay.
And so I just rewriting it, yeah.
Okay.
And try is like replace
Substitute,
all
yeah.
y's with whatever is the argument.
Yeah, and I probably should have given you that earlier, but I haven't. For some reason, I was going to wait on substitution product until tomorrow. So what is y? Well, let's do y to the y. No. Let's do some assuring things first. What's y to the a, where a is a set? And what's 1 to the p? Okay, so y to the a, it better be y to the a, otherwise we're in big trouble, right? Otherwise we have ambiguity in our notation that's too much to bear. But this says it's the product over all a in a, because a is q, of the sum over all positions of y, well there's one of those, the direction, and then directions of y, and then y plus q. Okay, what is this? What are the directions of this thing? 0. Y times y times y times y.
Yeah.
Okay, so that's fine.
Yeah.
Safe. And then similarly here, well, this thing says it's product over a over positions of p of 1 composed with some stuff. But I don't care what that stuff is because this is a constant functor. 1 is the constant 1. And so plugging into y doesn't do it. There is no y in there.
Right.
So this is just 1. So, yeah.
What does that underscore in parentheses mean?
It means what you want it to mean.
It
It doesn't matter. Throw this away.
P is, it always works.
This is a functional programmer's underline. What?
Okay.
Yeah.
Cool.
Okay. Okay. Okay, what's y to the y? It's product over one element set of y composed y plus 1. Did I do that too fast? I just read off this. The bottom line is easier. If you know triangle, the substitution product,
Yeah.
it's easier. The top line is a little heavy, a little like, yeah. So we just get y plus 1. So what's y to the a? Why don't you try that on your page or something? Okay, any guesses? Too fast. Y to the a plus a. That's a guess. Other guesses? Y plus a. That's a guess. So we're supposed to multiply up over all positions here. Well, there's just one. So this product is just a one-area product. There's only one. One plus.
One plus a.
So is it 1 plus a, y plus a?
What did you say?
Y plus a.
You said, didn't you say 1 plus a?
I got y plus a.
Y plus a.
Y plus a.
Yeah. Yeah.
I don't know how to calculate these. I don't understand what we're doing.
We're calculating them with this formula here.
Yeah, I don't know how to do that.
Okay. It says to take all the positions of this. That's what's written here. That thing up there is Q, right?
Which thing?
This guy.
That's in the cube, already cube.
Yeah.
And it says, okay, look over the positions of the Q. Well, there's only one. So we're just going to multiply one thing together. So we can kind of chuck that part. Okay, now we're here. It says R. Oh, well, R is just Y here.
Yeah.
So Y composed something. Chuck that part. Okay, then it says Y plus. Okay, we wrote Y plus. And then it said, tell me what the directions were.
Wait, why did we chuck the?
R?
Yeah.
Because the R is Y here.
So you're just taking.
Why are you keep looking up here?
I don't know. I'm trying to. I don't know. I'm going back and
Oh yeah, don't just watch
Well,
the thing
'cause
I'm
you thought
talking.
of why
Yeah.
the A and why the A, I don't know, I was just seeing.
Yeah, you keep not looking where I'm pointing. So Yeah.
Try pointing up then.
No.
Yeah.
So in that formula, it's like almost a polymap, right? Because it's like
Which one?
for the R to the Q. So it's for every
Oh,
position,
right. Okay, let's check
you
something.
choose a position. And
Yeah,
then
yeah.
For every direction, you either
So what are the
choose a
mapped-
direction or you don't need it.
The thing we said before was that always it'll be the case that if we look at the constants in this thing will be some big polynomial, but if we just look at the constant term,
Let's put in one.
it'll be poly QR. It'll be the maps from Q to R. So the constant term, how many maps are there from A to Y? How many maps are there in poly from A to Y? Well, if A is 1, if A is 0, there's 1. This thing agrees. And if A is anything else, there are none. And the constant term of this is, if A is 0, the constant term of this is 1. And if A is not 0, the constant term of this is 0. That was a little fast?
Yeah.
Yeah, it was fast? Yeah. It was okay? Yeah, so we just look at like this one was, the constant term of this polynomial, whatever it is, will always be the number of maps from this thing to this thing.
Makes me uncomfortable about this is that writing poly 1 to RQ is like really wants to be like picking a polynomial. As if
Polymaps, what are the polymaps from 1 to y cubed plus 3y plus 7?
What are they?
Yeah, how many are there? Not 11. 7. Yeah, because I need to pick any position I want, but then I have to take every direction to the empty set of directions.
Yeah.
Yes, exactly.
And I can only do that if I get the constant term.
Yeah.
So poly 1 comma blank just pulls out the constants.
Mm-hmm.
Just ask how many what are the constants of this? It's also, I mean, one way to say that it's obvious is that this is y to the 0 r to the q, or y to the 0 this thing. And the Yoneda lemma says plug in 0, which is the constants. Yeah. Okay, so the constants.
Could you say that again?
One way to see why it's obvious
Yes,
that this
yes.
pulls out the constants
Yes.
is that 1 is y to the 0.
Yes.
And the Yoneda lemma says that maps from natural transformations from y to the whatever to whatever
Yeah.
is just plug in 0.
Yeah.
And so that's the constant terms of that thing.
Yeah. Constant term
Of this polynomial here, whatever that might be.
Okay.
And so this fact that I wrote down that somebody said, maybe it was Andrea, said, why is this called the internal Hom? I said, well, one way to see it is that it's an internalization of Hom in the sense that it's internal because it's back in poly, and it's of Hom because we can extract the Homs by mapping in from the unit. And so when we map in from the times unit, because we're in the times closure, we're taking the constant term, constant term, yeah. And this gets to Max's point to just return, which is that this felt a lot like the maps from Q to R, because you say for every position in Q, pick a position in R, and then for every direction there, and you almost want to say pick a direction there, but then you say or Y. But if we plug 0 in, we're going to get back what we wanted.
Right. Yeah.
Yeah.
So R to the Q is like an example of the bracket.
Oh yeah, this is all closure stuff.
Yeah.
Bracket is the notation in general for a monoidal structure category, but our monoidal category we have lots of monoidal structures.
Yeah.
Infinitely many of them have monoidal closures,
Uh-huh.
and we're interested in 2 of them. And I reserve bracket for the one I like better because, I don't know, because I'm doing the class, I guess. And the one I use more often is the monoidal closure for tensor. Yeah.
So when you have the functor from poly to set
you recover the exponential?
Are you asking whether poly to set? The map from poly to what? Sorry, what are you asking?
So you go from poly to set, and now if you apply this functor to your exponentials in poly, what do you get at set?
Oh, I see. So you're saying is p to the q
Yeah.
of 1 equal to p to the 1? Well, this is exactly what I warned us about here. So no, it does not preserve exponentials. Yeah. Okay.
David?
It might be true of zero.
Exactly.
It might be true for 0, yeah. Yeah, p to the q of 0, I mean, someone who's not at the board should check. Who has extra cycles should check. Maybe that's true. I'll just put a little question mark over there. Yeah, Priya?
So why is y to the a not, so is it associative operation, like is it?
Oh, no, no. Exponentiation is definitely not associative.
Okay. So
Yeah.
it's not 1 plus a.
It's not what?
If I do y over
Y to the power y?
First.
Oh, I mean, so, right. So in general, you know, p to the q to the r is p to the q times r. But p to the q to the r, I was careful to put that in parentheses, is always a weird, you know, is always something that's kind of new.
Oh.
Yeah. Okay, so what is y to the power p? Well, I guess, I mean, instead of giving you the general one, because we've done all of them, they're all contained here.
Yeah.
But I mean, okay, what is y cubed plus 2y squared plus 1? Well, anyone know? You march through the sum ends, and for each one you write down this thing.
Uh-huh.
And you times them all together. So it's,
Uh-huh. Oh, that's,
Y plus 3
Yep.
times,
so times y plus 2 times y plus 2 times y, yeah.
to the 0.
Oops.
to the 0.
No.
That would break the pattern, right? Yeah,
No.
times y. I mean, of course we're supposed to multiply together when we add. We promised ourselves we would do that, right? We promised if we added in the exponent, we would multiply. So we just had to understand this one, and then we're done, really.
I don't understand that one.
Okay, you don't understand this one?
No.
Do you want to watch? Sorry, I'm gonna force you to just watch everything I'm saying, okay? I can't tell you otherwise. If
I
you
was watching before.
Okay,
I
okay.
didn't finish.
Okay, so we're here. This is R, this one's Q.
Yeah.
Okay. So we're supposed to multiply up over all positions of this one something. But this thing only has one position.
Right.
So this is a one-area product.
Okay.
And if you have a one-area product of some stuff, I can just not worry about it, right?
Yeah.
So I'm not worried about this anymore.
Okay.
Okay, now I'm supposed to sum up over all the positions of this one, because that's R.
Wait, sorry, say that again?
Now I'm supposed to sum,
Mm.
this thing is R, Y is R,
Yeah.
so I'm supposed to sum over all the positions of that one,
Yeah.
but there's only one.
Yeah.
So I'm going to do a one-area sum
Sure.
of some stuff. So I don't care about, I can chuck that one.
Okay.
Agreed?
Yeah.
Okay, so now I'm here.
Oh wait, but when you throw away the k,
The K is a unique position of this thing.
you just threw it away.
Well, I threw away caring about it.
Okay.
Because there's only one.
I'm doing a one-area sum.
Yeah. Right.
Yeah, so I'm going to have a tuple with one thing in it.
Yeah.
Okay, the thing that's in that tuple, that one-area tuple, will be this remaining stuff there.
Okay.
We're going to remember that K was the one thing there, and that J was the one position here. But we're not going to need to worry about these sum and product.
Say that one more time.
we're going to remember that j, when we see it eventually, we're referring to the one position here.
Yeah,
And that k, when we see it again, is referring to the one position here.
yeah,
But we're not going to care about the sum and productness anymore because we've already dealt with that.
yeah.
Okay, so now we're here. We're in R, which is the y thing.
Yeah.
And we're asking what are the directions of R at our unique position? Well, R was y. So what is R bracket k?
Wait, R. Okay, R is R bracket. It's Y. The A. Wait.
Nope,
No.
it's this guy's R.
Yeah.
And so what are its directions at the unique position?
Y to the A.
No,
Why?
R is y, and Q is y to the A.
Okay.
What are the directions of R at its unique position?
Oh, why? It's just. This one. I don't understand.
You do, you're just not saying it out. You just almost said it, you just stopped yourself.
One.
Yep, there's one direction.
Okay.
So we don't care about this. Okay, now we're here.
Okay.
So it's y plus, okay, what are the directions of Q at its unique position?
A.
Yep, so it's y plus A.
Oh my God. Okay.
Okay,
Okay.
okay, yeah.
Sorry, I understood it with the bottom one, which is kind of, in a way, sidestepping this, but
Yeah, the bottom one is maybe easier. So
But
so
you
it
don't
says
wanna try, though.
we don't know try,
How can you do that?
Yeah.
How can
so you
know it?
can't do it,
So you can't know
so
it.
you can't know it.
But some of us, I mean, some of us.
Some of us know it, so then they can do it.
So
Okay.
we can do it, but
Yep.
but the top one, I'm interested in what you just said, because you said R of K. There's
R
only
bracket
one.
K, because R is y. I mean,
Yes, R is.
yeah.
uh,
The only danger of this position is thinking that what you're looking at here is like y to the
yeah.
set. This is
Yeah.
not a set anymore. This is like,
Yeah.
so it's the only slight danger of this notation. It's nice in a lot of ways, but yeah, you can't quite
Okay. So is that
do you have this hand feel from doing
Yes.
polynomials so much,
Yes.
and the hand feel starts to break down a little bit with this notation.
Exactly.
Yeah.
And so could that be more safely written as y to the 1 all to the
Sure. If you
y to the a power?
yeah, maybe. Or you could just say it's r to the y to the a,
Yeah.
where you happen to know that r is y or something. But yeah, I don't know.
It's so like.
Yeah, y to the 1 to the y to the a if you want.
You've got.
Yeah, because like r is a
and then you
complete polynomial.
Yeah,
It's
yeah.
and so
It's
what's
not
the complete polynomial that's
Yeah.
being exponentiated? It's
yeah, y to the 1. Yeah.
That makes my heart sing.
Sing? Okay,
Yes.
not sink. Okay, good.
No,
Sing. Okay, great, great.
Yeah. Okay. Thank you.
Okay. So there are some pretty interesting things about this exponential, but they're a little bit more, I don't know, they don't feel like on the critical path, if you will. Like, so I think we should basically almost move on, but I just wanted to say, what is, there's an eval map. Well, I guess I could say a few more things. I don't know, yeah. Well, I'll just say, like, the very first day, or the day one, I gave you this. I asked you, what is the eval map like this? You didn't know it was an eval map, but this is y plus a, and the first day I said, what's the map from y times y plus a to y? Remember that? I gave you we gave 3 exercises, and for some reason I decided to give this one. It wasn't a very good exercise, but the reason I thought of it was because it's the eval map for. Do you see what's going on? How this is eval? Yeah.
Yes. Yeah.
So this eval, yeah. Yeah. I don't know. That's yeah.
Wow, that's cool.
Yeah.
So something.
What's
Oh, okay. Yeah.
what's y to the fifth
Yeah.
to the y? What do you say? Y to the 5y? Okay. Okay, what's that? I'm not sure if it helps.
It's y plus
Yeah.
1 to the 5.
Yeah.
Yeah.
So you get like these like binomial, how does this go? Uh-oh, 10? 1, 4, 6, 1, 5, 10. Ah, is that right? There we go. You get like these Pascal triangle, yeah, these binomial things, yeah. I don't know. It's a weird, it's a exponentiation. It's an internal Hom. If you, okay, so how many maps are there from y to y to the fifth? Well, it's the constant term. Yeah. Guess we knew that. But anyway, any questions on this?
So for the eval map for this, that ended up with.
Yeah.
I can check.
Yeah, what's the eval map?
I just
Take a position of this, this
So
thing
it's
is
like
y to the a plus 1 plus a y to the a.
Yeah.
Yep. So I need, for each position here, I need a position here. Well, okay, the unique one.
That's bang.
Bang, and then given a direction here, well, there's bang. One of them, so I need a
them.
direction of this.
Yeah.
Well, A could have been empty as far as we knew, so we know that if this is going to be a uniform thing, it's got to hit the 1.
Right.
And a map from AY to the A to Y is, yeah, kind of identity, yeah.
Okay.
Yeah. I mean, if you wanted, like, if you want exercises, if you want to give yourself exercises, you should prove this formula. I mean, like in a real math class, if we had a full semester, we would certainly prove this formula, right?
Yeah, I know that. I mean, I know that.
We'd want to prove
I
that.
don't see how. I don't
I mean, we even could do that. It's just we don't, like, that would be a use of time that we'd have to decide was worth it. But for any, it turns out for any monoidal structure on set, there is monoidal structure on poly.
Right.
Are you guys good? Should we continue? Okay. For any monoidal structure on set, there's a monoidal structure on poly that basically rewrites this whole thing and, sorry. For every monoidal structure on set, there's a monoidal structure on poly, and that monoidal structure is closed. And the closure will basically rewrite this whole thing and then put whatever your monoidal structure was on set, it'll put that symbol right there. The fact that times is the day convolution of plus is why there's a plus there. Here's another way to say it. The fact that times adds in the exponents is the reason there's a plus there. The fact that tensor times is in the exponents will put a times there. And for any of the infinitely many monoidal structures on set, there is monoidal structure on poly that, like, on positions just multiplies positions like we're used to. And on directions does your monoidal structure on set upstairs. Instead of plus or times, it does whatever other one there might be. And the closure for it will just put that monoidal structure here. So we're not going to use all those, so if you didn't really follow, it doesn't really matter. Unless someone's like, please, I really am super curious about what you just said. But, and that's fine, you really can do that. But I'll just move on to the times monoidal closure, or the tensor monoidal closure now.
Can you please repeat what you said?
Yeah.
Like,
Shall I repeat it or shall I write it?
yeah, right.
Right.
Okay.
For any
Okay.
monoidal structure on set.
It's a good thing you got there. Yeah. Okay. For any monoidal structure on set. Okay, so I'll tell you, I say there's infinitely many monoidal structures on set, but I'm not saying that there's infinitely many interesting ones. But I'll tell you them just so you know them, because otherwise I keep saying it. I'll tell you all the one, or I'll tell you an infinite class so that I can get it out of my, so I can at least discharge my promise or whatever. The promise is that for any, so there's all these maps from set times set to set. One is it takes a set A and a set B and returns A times B. But another is A plus B. And then here comes like the whole class of them. So A and B could be sent to A plus A times B plus B. And this one is surprisingly useful. Like, it seems weird to me, but like when I first saw it, but it's surprisingly useful. The monoidal unit is 0 for this one. But the infinite class is that for any set S, we could send AB to A plus S times AB plus B. And that's a monoidal structure on set. I'm not saying it's interesting. I've never found a purpose for any S. So when S is 1, we get this. And when S is 0, we get this. But you can also make S 2. And I've never seen a purpose for making S anything. I've looked for it and looked for it, like, why do you exist? But it doesn't ever want to tell me why it exists. Okay, so whatever your monoidal structure on set is, if you call it dot, I'll give you a monoidal structure on poly. So given dot, it's the day convolution.
So are you saying, you're saying day, D-A-Y, not
A man
D
named
comma-
Brian Day invented a way of taking monoidal structures on set and giving monoidal structures on, a way of taking monoidal structures on C and giving monoidal structures on functors from C to set.
Yeah.
Okay, so I'm going to tell you how that works for when C is set. So given this dot on set, I'll give you something called O dot on poly. That's going to be day convolution. You don't have to know what that is. You can go look it on Wikipedia or NLab or whatever. So it's going to take P and Q, and it's going to return a new polynomial, which is the sum over all pairs of a position in P and a position in Q of y to the P bracket I dot Q bracket J. And this will have a closure some weird shape that I need because I don't have enough shapes anymore. PQ is the product over I in P of 1 of Q composed, but we don't know what that means. So if you don't know what this means yet, sorry, you'll know tomorrow. Y dot P bracket I. And this symbol means, yeah. At least for all these, you will know exactly what this symbol means. So it's like, for this one, it would be like y plus pi, y plus pi for say this one. Okay. So that's what I said in words before. Every monoidal structure on set, of which there are infinitely many, gives the monoidal structure on poly, where you just, it's a distributive monoidal structure, so it, like P O dot Q plus R will be isomorphic to P O dot Q plus P O dot R. So for every monoidal structure on set, we get a monoidal structure on poly, happens to be distributive, happens to always have the same sort of positions. And the what you do in the exponents is whatever you said to do. And this thing will always have a closure, which is that thing. At least it has a closure in all these cases. That I assume I think it has a closure in all cases. But this dot, you have to decide that you agree this really does make sense. If you don't decide that, then I'll just say that these at least, you will be able to make sense of that dot. So
And that dot there, because that's in poly, that's like the
This dot here?
pointwise application to the output of the functors in set.
yeah,
Is that what that, okay.
yeah. Now, is that always a polynomial? I'll just say that for these, this
Yeah.
works. For these, this works.
Good.
Okay.
Sorry, can you please tell something about the thing in the bracket, like y dot p of I?
Yeah.
Is it like to the power?
No, it's this dot. It's whatever dot,
Okay.
given this dot.
It's a placeholder for some
Oh.
monoidal.
If this is bothering you, then
Pick one.
any of these, it shouldn't bother you. Because, well, pick one that's bothering you. One of the ones I told you you're allowed to pick. And I'll tell you how it works.
Okay, so maybe a plus b.
A plus b, okay, it means y plus p bracket I, and that is a polynomial. Okay. Whew, you picked an easy one, thank you. And if you picked times, I put a times, and that's just polynomial. If you pick this weird one, I give you this. And if you pick this weird one, I'll give you this. And those are all polynomials, so it's all fine in these cases. And there's some super weird polynomial monoidal structures on set. And for the ones that are listed in John Baez's question, what are all the monoidal structures you know on set, on Math Overflow? All of them make sense, and I think they all work. But I'm not promising that for every possible monoidal structure on set. It might be obvious. Maybe some people think it's easy. I don't know for sure, because I haven't checked it carefully.
Is there
Yeah.
a category where the objects are monoidal structures? And then-
Sure, yeah, that one.
And there's a
Yeah,
functor from
yeah, no, yeah. The objects are all the monoidal structures on poly, and the morphisms are the lax monoidal structure functors from one to another. I don't know if that's an interesting category, but it exists. Okay,
P of I is discrete polynomial.
P of I is a discrete constant polynomial, yeah. Okay, so the most interesting, from my point of view, in terms of like applications to machines and stuff like that, is the monoidal closure for tensor. So poly maps from P tensor Q to R are in bijection with poly maps from P to Q bracket R, where I have to define what that is. But I already told you what it is, because tensor was the day convolution of times. So, by the way, I didn't say this over here, but tensor, like I picked this weird notation of O dot for compared to dot, is like the, if you put times in here, you get tensor. And if you put plus in here, a lot of people in like vectors, in linear algebra will use plus to mean the product of vector spaces. So it's like you take plus here, you do this machine, you get times. You put times here, you do this machine, you get tensor. Okay.
time goes to tensor.
Times goes to tensor, plus goes to times. Yeah. Another fact, as long as we're over here, another fact, I suppose, that's pretty important is like, what is this whole day convolution thing about? It's that P of A, O dot, Q of B will universally map to P. No. These are sets. P of A times Q of B will universally map to P O dot Q of A dot B. That's a thing I've written a bunch of times in a bunch of forms. I've said things like P of A times Q of B maps to P plus Q. What?
What did you do in the top row? You
P times Q of A plus B, and P of A times Q of B maps to P tensor Q of A times B. So these are like universal, like day convolution says, I'm going to day convolution, this magic thing I've told you about but never defined, is like the universal acceptor of like the universal thing that fits into this formula, this pattern. times is over here, the monoidal structure you want of any form over here, and like this, the day convolution of this thing here.
And this map comes from,
Day convolution is created such that it works.
but what is the map? Like where is
Yeah, what is the map? Okay, I mean, well,
It's just what comes with the lax monoidal functor.
it just, yeah. I can't go into how this works. I could do it for Poly, how this works. Yeah, yep,
Sorry, I've somehow become quite lost.
okay.
So could you help me say, so at the top there on the left are various types of monoidals, are various types of monoidal
Structures on set.
in set.
Yeah.
And
I can multiply sets, add
Yep.
sets, do a weird thing to sets, and
Yep.
do an even weirder thing to sets.
And from those, one induces, from each of those, there's an induced monoidal structure on Poly.
Yep. And do-
That is corresponding but not the same. It's
I mean,
it's
it
not
can't be the
always
same because it's on a different category.
Yeah,
Yeah,
yeah, it's adapted systematically
yeah.
to reflect that, and you wrote.
Well, here's a fact.
down-
Y to the A,
Yes.
O dot, Y
Yes.
to the B
Yes.
will be Y to the A dot B. And then do positions. That's all that's happening.
I'm sorry, but the top one
Is a Poly thing.
is a Poly thing.
The bottom one is a set thing.
It's a set thing.
Yeah.
That is invariant. That one.
For all of these, this
All
will
of
happen.
Yes.
And then positions just say like,
Right.
you know, cast out, like you have a position from each, and then you're ready to do
Yeah.
this. Yeah.
Yeah, and the like the what is the identity? That's not
Oh,
the right way
the identity here is always
No.
Y to
yeah,
the unit here is always Y to the unit of this one.
yeah,
So this one will have unit Y to the 1.
yeah.
So the unit for tensor is Y. The unit for plus, or for times is Y to the 0, etc.
Okay,
Yeah.
so, but if we consider a given dot.
Yeah.
That's used in the A dot B.
Yeah.
The corresponding circle dot is given by day convolution.
Yeah. Is a convolution of
Okay, dot.
of O dot of dot. Yeah.
Yeah, so it's not like immediately you look at the dot and you say, I know, like I always know immediately what it is in Poly. It may be sort of a funky one, but it corresponds to it.
Well, it's exactly this one.
I guess you wouldn't know
Yeah.
if you knew what day convolution
Yeah, yeah.
was.
If
sure.
you knew what day
would
convolution
know.
was, you'd like march through some things, and then you'll be like, oh, this looks hard, and then like something would open up in your mind, and you'd be like, okay, maybe if you're lucky,
Yeah,
eventually opens up, and then you're like, yay, and then you realize everything falls
Yeah.
away, and you get this pretty formula.
okay, the pretty formula.
If you consider this pretty,
Yeah, So,
Yeah.
so that pretty formula gives us what?
This gives us a monoidal structure on Poly,
Yes.
which for any
Yeah.
dot on set.
Dot
And there's
on
only
set.
two pretty interesting ones on set, like maybe 3, but 2. One is times and one is plus, and they give us tensor and times.
Yep.
Okay.
Poly,
Oh,
this is a thing of delight too.
oh, sorry. No wonder this was confusing.
Okay. That's just gorgeous.
Okay, Priya.
One question. So, the thing on the top right, like it says, like, is it always times P of?
Yeah, these are all day
times?
convolution for set times. Yeah,
Just
I mean,
times.
yeah, times.
Always times.
Yeah,
Okay.
always times. Yeah,
Okay.
yeah.
Is times Cartesian
Product of sets. Yeah. In fact, yeah, even more is true. Maybe we should say this because I was like, oh, I'm not going to get to say this really cool thing. So I guess I'm gonna say the really cool thing. Where do we lose it? Oh, there it is.
Sorry, can I?
Yeah. Yeah, did someone else have another question?
Yeah, I just got confused that you said that those are deconvolution for the times, but I thought that they were Convolution for whatever the monoidal structure
Yeah.
on the set. On the
Tensor is the deconvolution of times.
I guess
Like
tensor-
classic,
yeah,
like-
yeah, yeah, but so only the third one is the deconvolution of times in those
So why is
on
it
the
that
top
you
right.
use, in the upper
In
right hand
top
corner,
right,
David,
yeah.
why
Yeah.
do you always use?
Sorry, did I say, I must have said something wrong. Deconvolution is about functors from C to set for any category C, for any monoidal category C. It assumes the Cartesian product on set. That's what I meant to say. This is coming from the fact that the way deconvolution works has to do with Cartesian monoidal structure on set.
Right. Okay.
Yeah. Yeah.
But each of the ones on the right are different.
Yeah, these are the deconvolutions of different monoidal structures on set. Yeah.
Gotcha.
And the thing I wanted to say that it probably won't be, these are just, yeah, let me just write this thing. P1, I know we don't have this symbol yet, sorry, anyone. P1 times Q1 compose, Q2 maps to P1 tensor Q1 composed P2 times Q2. So what I'm saying here is, here A and B were sets, but I could have applied a functor before I got I could have gotten those sets from applying a functor. And yeah. I just really like these two facts. These are really interesting and surprisingly useful facts that I just wanted to write so that I could say I wrote them tomorrow, if I ever want to. These come from the deconvolution idea also. So, yeah, sorry that I wrote these facts that just look kind of mysterious, but hopefully one day you care. Yeah.
So if dot in set
Yeah.
is symmetric monoidal,
Yeah.
is circle dot
Yes.
symmetric monoidal?
Yes. Yeah.
In poly.
Yeah.
Joy,
Yeah.
happiness.
Great.
Just great.
Yeah. Okay, shall we go on and talk about this internal hom? Yes.
I just wanna, you've got like 15 minutes before 4 o'clock.
Okay. Okay, so we'll have to decide if we want to stop for the day at 4 or keep going. Yeah, okay. So QR is a polynomial, and it's, I already gave you the formula, but let's write it anyway. It's the product over positions of Q. For every position of Q, pick a position of R. And then for every direction there, pick a position of Q. And then put a Y. That turns out to be the same as the formula I wrote over there. So another way to write this is we can distribute some stuff. And it turns out to be that the positions now, okay, what's great is that we know that polymaps from now Y to QR are what? Anyone remember why I'm writing this? QR is an internal hom.
Yeah.
And if you want to if you probe the internal hom with the monoidal unit, something good happens. Do you remember what it is?
It's the hom.
Yeah, it's polymaps from P to Q. Well, we're way more interested. This is the same thing as, what's that? What's polymaps from Y to something?
In QR?
Yeah.
What's polymaps from Y to anything?
On the right-hand side, you mean QR?
It's a choice of position.
Yeah.
Yeah.
So we're way more interested. We're almost always interested in the positions.
Yeah.
For the exponential, R to the Q or whatever, we were looking at the constant terms, which is kind of like a little bit unusual for us. We're usually looking not at the constant terms of a polynomial, but at all the positions of the polynomial. And so here, the positions of this polynomial really are the maps from Q to R.
Yeah.
So it's a sum. The positions are a map from Q to R. All this stuff here, until you get to the y. If you plug in 1 for y, you just can count. You can just read that this says, for every position in Q, pick a position in R, and for every direction there, pick a direction there, and stop. So polymaps from Q to R are exactly this, where you plug in 1 for y. For every position in Q, pick a position in R. For every direction there, pick a direction back there. So now we just need to say what this is. Y to the power. So
Oh my goodness.
what, okay. Y to the power, well, one of these and one of these, basically. J in Q of 1, R bracket. Okay, so this might look complicated, but it's saying that a position of this is a map from Q to R. And what's a direction there? Well, if you have a map from Q to R, then you have a way to take positions of P to positions of Q to positions of R, and directions of R back to directions of Q. So all the data you would need for a position and directions of both would be a position of Q and a direction of R. What am I saying? If you had a position of Q,
Polybox thing.
if you had a position of, yeah, we have in hand now this map. We have a position, so we have a map from Q to R. And if you wanted all the data of like all 4 boxes to be filled in, you would need to fill in this one, then you'd get an automatic one there, and you'd need to fill in this one, and you get an automatic one there.
Given map,
Yeah. And so this says, okay, I want to know the position here, and I want to know the direction there. And I'll have all 4 pieces of information. So those are the directions that it says to use.
So it's intuitively obvious.
Just intuitively, once you see what it is, you're like, oh, I always hoped it would be you. But you didn't know who you hoped it would be until you met them. Okay.
I don't get it.
Okay. Do you get that it's kind of cool that the positions of this thing are the maps from Q to R?
Yes.
Okay, and why that's true?
Yes.
Because we plug in 1 for y.
Yeah.
Okay. And now we're just interested in the directions. And so someone's given us a map from Q to R.
Yeah.
That's a position of this thing. What are the directions of this thing? They've given us a position. They've given us a map from Q to R. What are the directions? A direction will be all the data you would need to know everything about. I don't know. Let's go. Let's just say what it is. A direction is a position in Q and a direction at its image in R.
Oh, right, yeah.
And then from that, you could also recover a position in R, because you just apply your map phi. And you could also recover a direction in Q, because you'd do your phi sharp, your map back.
Right.
Yeah.
Can you tell me what's that character between the P2 and the Q2 at the top?
Times.
Above that. Is that a times?
Yeah.
Okay, thank you.
Yeah. Okay. Okay, so I guess I wanted to say, like, why? Yeah. Yeah. Maybe we should do some examples. Oh, did I erase? Why did I erase that? I don't know. Oh, I see. QR of 1.
Thank you.
It's about 30 seconds.
Okay. 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 Questions?
Why is it useful? Why?
Why is this useful? Yeah. Yeah.
That's a
Okay.
good question.
Okay. So.
Yeah. Yeah. I guess it's interesting to look at PQ coalgebras. Okay? That's
There we go.
like that's the main thing that I am stuck on in
Okay,
Poly, and I'm
great.
running on fumes now.
Okay.
So
Then, yeah. Do you need some energy? There you go. Here. There's another one. Okay.
Okay, that is,
Okay.
can be destroyed if you so
Okay.
please.
Okay.
Are we going to talk about them more, or?
PQ coalgebras? I think today's our main day for it. Okay. Okay. So remember we were all about like machines, right? We were talking about like you've got some wiring diagram and like some stuff's happening and all this stuff, right?
Mm-hmm.
And so maybe this one is A and B and C and D, and we wrote down a map from CY to the AB tensor, DBY to the C to DY to the A, that this diagram is. Okay. But like it's annoying, like it's kind of annoying that this wiring diagram is stuck for all time. We've got these machines. Okay, so you're this machine and I'm this machine, and you're sending me this data, I'm sending you this data, and the world can kind of see. I can look out into the class and see other people, and then the class can hear me or whatever, right? Okay, but we're just stuck like this forever. Like I'm always going to talk to you for all time. Like in a circuit, like it's just soldered into the material. But like in life, we can move around, and sometimes you're talking to me, and sometimes you're talking to somebody else. And so you might have like all these things in here, and they should change who they're talking to. But how do we decide when to change who we're talking to? Well, we decide based on like what we see and hear, right?
Yeah, it's based on the states of the.
It's based on the states of what's inside of us and what's coming into us. Like what we see from each other. Like if I say, okay, bye, and you hear that, then you're allowed to use that in how you change, right?
Yeah, you're talking like.
We talk in this pattern, and then we decide, okay, let's cut this wire and flow this out there and have that go there or something.
Wait, but now you also change the outputs of
Yeah.
of everything.
Yeah.
Okay.
Yeah.
I thought you were talking about changing the wire pattern.
Well,
inside.
yeah. You're right. Okay. It's true that the way I set it up, you're right. But if you allow these things to be polynomials that are not monomials, like where the box can change its input and output type, then what I did would have been legal.
Okay.
Okay. So that's what this thing is going to do. Like P1 tensor, you have all these things talking to each other and talking to the outside world or something. And you want this arrow itself to change. You want the wiring pattern itself to change through time. And so that's what this thing is going to do. It's saying, I don't just want like one map. I want a polynomial for every state. It depends. Yeah, some people like the coalgebra version better. Some people like the S version better. But okay. What? Did someone say?
Goal, but I think I know what this is going to go when eval comes in.
Eval, interesting. Okay, okay.
It's going to be the wiring diagram that takes something that has a wiring diagram as a state and makes that happen.
Yeah, probably, yeah.
Like a eval
Okay.
a la Poly.
Sorry.
Yeah. Okay, so what is one of these? Whether you like a coalgebra version or the SYDS version. Okay, so what is one of these things? It says for we have some machine with some state. Every state is going to give us a position of this. What is the position of this? It's a map, right? It's a polymap from this tensor to this.
Yep.
Well, that's exactly what this is supposed to be, right?
Yeah. Right.
So for every state, we get a different wiring pattern.
Right.
So this thing's marching through states, giving us wiring patterns.
Yeah.
But how does it update its state? It updates its state based on a direction here.
Yes.
So what are the directions here? A direction here will be a position of all these guys. In other words, an output of all these. So it'll be the information in green.
Things flowing on the right.
It'll be all the outputs. together with the inputs here, the directions here. But the directions here are the inputs there.
Yeah.
And once you have the green stuff, you have everything in the wiring diagram.
Because the maps from the inside to
Right,
the
exactly.
outside.
Yeah.
So in other words, the way you're allowed to update your state is based on what is flowing through the wiring diagram.
Yes.
Okay. But this is still, it's still, like, the output to the outer box is still fixed, right?
Well, it depends what Q is. If Q is y,
If it's
d
autonomial.
y to the a plus d prime y to the a prime, then for certain states, you could be, and for certain output to these guys, you could be in this situation.
Okay,
Yeah.
And where does S
Yeah, it's cool.
live in terms of, like, how would you draw S?
This is
S is a state machine that just, like, S is, oh yeah, the way that Sophie and I draw S is a green squiggle. Actually, it was originally an orange squiggle. Of like something is controlling this thing.
Okay.
Yeah. It's like the CEO of the company or whatever. You know, it's like so in machine learning, this will be the gradient descent procedure.
Yeah.
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 In prediction markets, this will be Bayesian update of predictors or whatever.
But
This is a thing that listens to what everybody does. It listens to the outputs of all your neurons, and then the loss or whatever, and like makes a change in weights.
yes.
Yeah.
What's that character to the left of that diagram?
Phi.
Is that a phi?
Yeah.
Okay.
Okay. This feels like it should be reasonably straightforward to
Implement?
get a list of states.
Yeah. This is the thing. This is the thing that we talked about on the phone call.
Yeah.
Yeah.
oh, this is so cool. It's just,
Goal.
yeah.
Nice. Cool.
Yeah.
It's kind of like, it feels kind of like you're taking your polymaps and turning them into like data structures that you can then manipulate and then evaluate
Yeah.
or something. Like
Yeah.
you're defunctionalizing your polymaps or something.
I don't know those terms, but
I don't know.
it's
Sounded good.
sounded good. Sounded yeah. But yeah, you're internalizing polymaps as the positions in something.
Yeah.
And luckily, the directions we also care about. They also make sense.
But I think actually, David, from your point of view, you're a
Yeah.
mathematician and you see how dynamic the world is. As to your point, as you introduced this, you said, well, we can make choices about how we interact with one
Yeah.
another, and we do that all the time. So
Yeah.
we adapt depending upon our state.
Yeah.
We I'm going to go get on a plane, I'm going to go home, and I'm
Yeah.
going to interact with my wife and
Yeah.
people at home and make phone calls to the folks back in Pennsylvania. We do that all the time.
Yeah.
We change our wiring diagram.
Yeah.
I have a question, which is, it might be just because I'm really tired, but when you get like sy to the s, just regular map to some polynomial that is a sum,
That is a sum. Yeah.
yeah,
hmm
you already have changing wiring patterns.
Wiring patterns. Why would you call an arbitrary polynomial? If you had sy to the s to p, why would you call positions here wiring patterns?
No, you're not calling it, it's not position, but this map already describes a mode-dependent dynamical system.
No, well, so let's say p is y cubed plus 5y squared plus y or something. Okay. So yeah, for every element of S, we either get something with 3 inputs, or we get an output of 1 through 5, and we are waiting for 2 inputs or whatever. Yeah. Yeah.
So, but here so what is the difference from that, from just something like this, to?
It's that the difference between an arbitrary p and then this p is that this p we have more data about where we got this p. I mean, this p could have been this p. This p could have been this. Yeah, it's true. But this one where we have some syntax that tells us like, no, I got this P from something. It is the
Right.
internal HOM of something.
Uh-huh.
And so we have more fine-grained understanding of what the positions of this, feel like and what the directions are.
You could
Okay.
build dynamics on this guy too, right? So you could put, for each of those PI, I goes from 1 to N.
Yeah, that's true.
You could
Yeah.
put an S1, Y.
I
and
see.
S1.
Yeah, I see what you guys are talking. Yeah, I see what Max was saying now, I
Then-
think.
You have this another layer, right?
Yeah. I mean, this forms
All
an
of the stuff
operad,
in the bottom and then
Yeah.
plus the
Yeah.
stuff in the top that can be rewired.
a poly-enriched operad,
Subsequent
yeah,
interact.
or multi-category, yeah.
Yeah, no, I'm just saying, what I'm trying to, like, you don't get, if that, yeah, if P is an arbitrary polynomial,
Yeah.
you have just as much expressive power in the sense of like the kinds of dynamical systems that you can express are not different from if you're treating them as a HOM, as an internal HOM.
I mean, if you have A times B, you can project out to an A. But you could say, oh, well, I could take X to A too. It's true. But I mean, this one,
Yeah,
yeah.
I get it.
With this one, you could evaluate. You could tensor it with P1 tensor, or even a subset of these. But you could tensor it with this and move into a Q or something. Like there's more data in this. Like there's more, because you have some syntax here. You're ready for more action.
Right,
Yeah.